Part 1. The Golden Enigma. Something impossible has happened in the skies above us. A comet, radiant with a surreal golden light, has fractured into fragments, each trailing a stream of debris through the void. The celestial body, now splintered, glimmers like a cosmic firework frozen in time, its shards reflecting the distant sunlight in hues of amber and bronze. Astronomers have never witnessed anything quite like it, a comet that gleams gold instead. Of the familiar icy blue-white. But here's the twist. This comet, the one you've been watching in awe, isn't the interstellar visitor it's been touted to be. Two separate cosmic events have collided in public perception, creating a narrative that doesn't actually exist. This is a story of mistaken identity, of spectacle versus reality, and why untangling the truth matters more than you might think. The Golden Comet, now dubbed C2023 G1 first, appeared in the night sky 6 months ago, a brilliant streak against the backdrop of the Milky Way. Its discovery sparked global fascination, with stargazers and scientists alike marveling at its unusual trajectory and coloration. News outlets declared it the most spectacular comet of the century, drawing comparisons to the legendary Halley's Comet and the Great Comet of 1811, which dazzled the world with its brilliance. Social media feeds flooded with images of the golden streak captured by amateur astronomers and professional telescopes alike. Yet, unbeknownst to the public, another comet, one far more extraordinary, was hurtling through the outer reaches of the solar system, hidden in the shadows of its more flamboyant counterpart. What we know versus what we don't. Known. 2 comets, one interstellar, one from our solar system, are currently active and observable. The Interstellar Comet. Designated I-2023-01, originated from beyond our solar system, travelling at a staggering 30 kilometers per second. Its chemical composition suggests it formed in a system vastly different from our own, offering scientists a rare glimpse into the cosmic processes of distant stars. Meanwhile, the Golden Comet, C2023 G1, is a long-period comet from the Oort cloud, a spherical shell of icy bodies at the edge of our solar system. Its golden hue is believed to be the result of a unique mixture of minerals and organic compounds, though its exact composition remains a mystery. Unknown. Why their stories became entangled and how to correct the confusion in public perception. The misidentification began with a misinterpreted tweet from a prominent astronomer who mistakenly linked the Golden Comet's appearance to the trajectory of the interstellar visitor. Within hours, the error spread across social media, amplified by headlines proclaiming, "Interstellar Comet turns gold." By the time the correction was issued, the narrative had already taken hold, fueled by stunning images and viral videos of the Golden Comet streaking across the sky. Observation. The power of spectacle. The Golden Comet's visual splendor has overshadowed its less flashy interstellar counterpart, highlighting the human tendency to gravitate towards spectacle. While I-2023-01 represents a scientific breakthrough, its faint, distant glow pales in comparison to the golden radiance of C2023 G1. The discrepancy raises questions about how we value and prioritize information in the age of viral media. Are we more captivated by the beauty we can see than the mysteries we cannot? Interpretation. The cost of confusion. The conflation of these 2 comets is more than a harmless mix-up. It underscores a growing disconnect between scientific accuracy and public understanding. Misinformation, even when unintentional, can erode trust in scientific institutions and skew public perception of critical discoveries. For example, the interstellar comet's arrival offered a once-in-a-lifetime opportunity to study extrasolar materials, yet much of the public remains unaware of its significance, fixated instead on the golden spectacle. This disconnect has real consequences. As funding and resources are often tied to public interest and engagement. Speculation, the future of the Golden Comet. As C2023 G1 continues its journey through the inner solar system, scientists are racing to unravel the secrets of its golden hue. Some theories suggest the presence of rare metals or complex organic compounds, while others propose that the comet's unusual color is the result of intense radiation from a nearby star. Whatever. The cause, the Golden Comet's fragmentation, will likely intensify in the coming months, creating a celestial show unlike any other. Meanwhile, I-2023-01 will silently slip past the Sun, its interstellar origins a whispered secret among the stars. The Golden Comet's story is far from over, but its legacy is already written in the skies. It has reminded us that beauty and truth are not always aligned, and that the things that captivate us are not always the things that matter most. As we marvel at the golden fragments streaking through the cosmos, we must also turn our gaze toward the quieter wonders, the ones that challenge us to look beyond the spectacle and into the unknown. Part 2. The Viral Spectacle. Imagine this, a comet glowing like liquid sunshine, its tail spreading across the darkness of space like a cosmic brushstroke. Then, just days later, it shatters into distinct pieces, each trailing its own luminous debris. Astronomers across the globe were stunned by the spectacle, as were millions of people who had never before turned their eyes to the night sky. This is the story that's dominated headlines and social media feeds for weeks. It's visually stunning, emotionally captivating, and scientifically fascinating, but is it true? The images are undeniably breathtaking. Amateur astronomers and professionals alike captured the comet's golden hue and fragmentation in vivid detail. Social media platforms exploded with hashtags like SARC Golden Comet and SARC Cosmic Breakup, generating over 12 million posts within the first few days. News outlets featured the comet on their front pages an evening. Broadcasts led with dramatic headlines like, "The sky is falling, or is it?" Celebrities, influencers, and even politicians weighed in, sharing their own photos and theories. The comet became a cultural phenomenon almost overnight, inspiring memes, merchandise, and even a viral TikTok dance called the Comet Crumble. But here's where the narrative splits from reality. A comet did turn golden and fracture into multiple fragments, but it wasn't the interstellar visitor everyone thinks it is. The actual interstellar comet, 3I Atlas, looks completely different. Discovered in 2023, 3I Atlas is a faint, unremarkable object to the naked eye, moving through the solar system at a staggering 175,000 miles per hour. Its composition is unlike anything in our solar system, containing isotopes and organic compounds that hint at its origins in a distant star system. Yet it lacks the visual drama of the comet that captured the world's attention. Observation: the comet that went viral is actually a lesser-known object called C2025K1, nicknamed the Golden Comet by astronomers. C2025K1 is a long-period comet, meaning it originated in the outer reaches of our solar system and takes thousands of years to orbit the Sun. Its golden color is the result of a rare combination of minerals and gases in its composition, which reflects sunlight in a way that creates a brilliant, almost metallic sheen. When C2025 K1 fractured, it was likely due to the intense heat and gravitational forces it experienced as it approached the Sun. This process, known as nuclear fragmentation, is not uncommon among comets, but it is rarely witnessed in such dramatic fashion. Speculation. How did millions of people end up watching the wrong comet? The answer lies in a collision of timing, naming conventions, and the way. Information spreads in the age of virality. In the summer of 2025, both 3I Atlas and C2025 K1 were visible in the night sky, albeit in different regions. 3I Atlas was the subject of intense scientific study, as it is only the third interstellar object ever observed in our solar system. Meanwhile, C2025 K1 was largely ignored by the scientific community until its sudden fragmentation. The public, however, latched on to the spectacle of C2025 K1 and the confusion began. The misidentification was likely exacerbated by the similarity in the names Atlas and K1. Both comets were discovered by the same observatory, the Atlas project in Hawaii, which led to further confusion. Social media algorithms amplified the mistake, as posts about Atlas and the Golden Comet were often grouped together, creating a tangled web of misinformation. Within days, the narrative had solidified, the golden fragmenting. Comet was believed to be the interstellar visitor, and the truth was buried under layers of viral content. The consequences of this mix-up are significant. While the public's fascination with C2025 K1 has sparked a renewed interest in astronomy, it has also overshadowed the scientific importance of 3I Atlas. Funding for research into interstellar objects is already limited, and the misidentification has made it even harder for scientists to secure support. Meanwhile, conspiracy theories have flourished, with some claiming that the fragmentation of C2025 K1 was caused by alien technology or government interference. These theories have gained traction online, further muddying the waters of scientific communication. Yet, there is another side to this story. The viral spectacle of C2025 K1 has inspired a new generation of stargazers. Telescope sales have skyrocketed, and astronomy clubs have reported record membership numbers. Schools across the globe have incorporated the comet into their science curricula, using it as a teachable moment to discuss everything from orbital mechanics to the chemistry of comets. In this way, the misidentification has had an unintended positive effect, reigniting the public's curiosity about the cosmos. The story of the Golden Comet is a modern parable about the power and pitfalls of virality. It reveals how easily information can be distorted in the age of social media, but it also shows the enduring human fascination with the mysteries of the universe. As scientists continue to study both C2025 K1 and 3I Atlas, the truth will eventually emerge. Until then, the Golden Comet will remain a symbol of our collective wonder and our capacity for belief. Part 3. The Golden Comet, C2025 K1 Atlas. Let's start with the comet you've actually been watching. Officially designated C2025 K1 Atlas, this object made an extremely close approach to the Sun in early October, diving within 27 million kilometers of its blazing surface, a distance less than 1/5 of Earth's average proximity to the star. As it ventured into the inner solar system, solar radiation vaporized its surface ice in minutes, triggering a massive outburst of dust. The dust, rich in certain minerals, reflected sunlight in a way that created a luminous golden hue, a sight so rare and beautiful that it captivated the world. Amateur astronomers and professional observatories alike documented the comet's transformation, as its coma the nebulous cloud of gas and dust surrounding its nucleus, expanded to nearly 5 times the size of Earth. The golden color wasn't just aesthetic, it was evidence of a specific physical process. Sunlight interacting with dust particles containing iron or other metals created this warm, otherworldly glow. The fragmentation, captured in real time by astronomers, revealed structural weaknesses in the comet's nucleus, cracks that had been widening under thermal stress and outgassing pressure. These fissures, some barely a meter wide but stretching kilometers in length, acted like fault lines, slowly disintegrating the comet's core. As the comet's icy body heated unevenly, plumes of gas erupted like geysers, further destabilizing its fragile structure. Microhook. Imagine a comet surviving a perilous brush with the sun, only to fracture days later as internal damage accumulated during its closest pass. This is the story of C-2025 K1 Atlas. Observation. During its closest approach, the comet's surface temperature soared to over 600 degrees Celsius, hot enough to melt lead. Yet, beneath this scorching exterior, the comet's interior remained frozen, a relic of its long journey from the outer solar system. This temperature disparity caused the comet to behave like a cosmic pressure cooker, with volatile compounds trapped beneath the surface exploding violently as they heated. Astronomers observed jets of carbon dioxide, water vapor, and even traces of complex organic molecules spewing into space, painting a vivid portrait of the comets. Chemical makeup. Speculation. Some researchers hypothesized that C-2025 K1 Atlas might have originated from the Oort cloud, a vast spherical shell of icy bodies far beyond the orbit of Neptune. If true, this would mean the comet had been traveling for millions of years, slowly nudged from its distant home by the gravitational influence of passing stars or the Milky Way's tidal forces. Its golden outburst, then, was not just a spectacle, but a fleeting glimpse into the primordial material that formed the solar system billions of years ago. The comet's disintegration was both tragic and scientifically fascinating. As fragments broke away from the main nucleus, they scattered along the comet's orbit, creating a trail of debris that stretched for millions of kilometers. These fragments, glinting like embers in the sun's glare, were studied intensely by astronomers, by analyzing their composition and trajectories. Scientists hoped to reconstruct the comet's history, a cosmic autopsy of sorts. Some of the larger fragments even survived long enough to develop their own tails, miniature comets born from the death of their parent body. Interpretation. The fragmentation of C-2025 K1 Atlas was not a sudden, catastrophic event, but a prolonged process. Over the course of several days, the comet shed pieces of itself like a dying star shedding its outer layers. This slow-motion breakdown allowed astronomers to study the comet's internal structure in unprecedented detail. They discovered that the nucleus was not a solid, uniform object, but a loosely bound agglomeration of ice and rock, a dirty snowball held together by gravity and the weak bonds of frozen gases. As the comet crumbled, it revealed layers of ancient material, each one a chapter in its icy autobiography. For the public, the comet's demise was a bittersweet spectacle. Social media platforms were flooded with images and videos of the fragmenting comet, its golden hue fading as the dust dispersed. Hashtags like "Struck Your Golden Comet" and "Farewell Atlas" trended for days, with users sharing their final glimpses of the celestial wanderer. In some cities, impromptu comet-watching parties were organized, with families and friends gathering on rooftops or in open fields to witness the comet's last moments. For many, it was a reminder of the fleeting beauty of the cosmos, a celestial firework that burned brightly before fading into the void. Speculation, some astronomers wondered if the comet's fragmentation might produce a meteor shower in the coming years. As the debris spread along the comet's orbit, it would eventually intersect with Earth's path around the Sun. If enough material survived, it could create a dazzling display. Of shooting stars, a final tribute to C2025 K1 Atlas. Others, however, were more cautious, noting that the fragments were likely too small and dispersed to pose any significant threat to Earth. Still, the possibility of a future encounter lingered in the minds of scientists and stargazers alike. As the comet faded from view, it left behind a legacy of scientific discovery and public fascination. Astronomers had gained valuable insights into the behavior of comets under extreme conditions, while the public had witnessed a once-in-a-lifetime event. For a brief moment, the Golden Comet had united people across the globe, reminding them of the wonder and mystery of the universe. And though C2025 K1 Atlas was gone, its story would live on in the data it left behind, a cosmic tale written in stardust and ice. Part 4. A Close Encounter with Destiny. C2025 K1. Atlas wasn't supposed to survive its close solar pass. Most comets that venture this near the Sun simply disintegrate or fade from view within days. The Sun's intense heat and radiation can vaporize ices, crack the comet's nucleus, and scatter its fragile structure. But this one defied the odds. It emerged back into observable range, its golden tail spreading out in a graceful arc that stretched millions of kilometers across the night sky. Astronomers worldwide tracked its trajectory, their telescopes capturing the eerie beauty of its resurrection. Then, on November 11th, they watched in real time as its nucleus began to break apart. The comet's brightness flickered, a telltale sign of structural failure. By the following night, the fragmentation was unmistakable. Multiple distinct pieces, each trailing its own debris. The fragmentation process was both violent and delicate, a ballet of destruction visible only through the most powerful observational tools. Observatories like the Large Binocular Telescope in Arizona and the Gemini Observatory in Hawaii captured the event in stunning detail. The images revealed fractures in the comet's nucleus, glowing faintly as sunlight reflected off the escaping gases. Each fragment, no larger than a few hundred meters across, began to drift apart at speeds of just a few meters per second. These fragments, once part of a single cohesive body, were now independent travelers, each on its own journey through the solar system. Observation. The fragmentation wasn't explosive but gradual, with pieces drifting apart as their individual outgassing created slight differences in trajectory. Each fragment developed its own small tail, contributing to an expanding debris field. The debris field itself was a spectacle, a sprawling cloud of ice and dust that glinted like diamonds against the black void of space. Astronomers measured the field's expansion over the following days, calculating that it grew by nearly 10,000 kilometers per hour. The fragments, meanwhile, began to diverge more significantly, their paths altered by the gravitational influence of the Sun and the subtle nudges of their own outgassing. Speculation. Will these fragments survive as distinct objects, or will they break? Down further into smaller pieces, time will tell, but astronomers are watching closely. Every bit of data helps refine our understanding of comet structure and behavior. If the fragments remain intact, they could provide valuable insights into the composition of comets, which are often described as time capsules from the early solar system. However, if they disintegrate further, they may offer clues about the limits of cometary stability, particularly for objects that venture dangerously close to the Sun. What we know versus what we don't, an unknown. See 2025. K1 Atlas fragmented into multiple pieces after its closed solar pass. The fragments are currently traveling on slightly diverging trajectories, creating a growing debris field. Unknown. Whether these fragments will survive as distinct objects or disintegrate further. It is also unclear how long the debris field will remain visible, or how it will interact with other celestial bodies in its path. The fragmentation of C2025 K1 Atlas raised more questions than answers. Scientists are now debating whether the comet's structure was inherently weak, or if its close encounter with the Sun triggered an unavoidable breakdown. Some theories suggest that the comet's composition, a mix of ices, dust and rock, made it particularly vulnerable to solar heat. Others argue that the comet's age played a role, with older comets being more prone to fragmentation after repeated solar passes. Regardless of the cause, the event has reignited interest in comet research, with teams across the globe analyzing the data in hopes of unraveling the mystery. One of the most intriguing possibilities is that the fragments could reveal the secrets of the solar system's formation. Comets are believed to contain materials that date back to the birth of the Sun. And planets, frozen relics that have remained largely unchanged for billions of years. If astronomers can study the composition of the fragments, they may uncover clues about the conditions that existed during the solar system's infancy. This could include the presence of organic molecules, which are thought to have played a role in the emergence of life on Earth. The fragmentation also has practical implications. As the debris field expands, there is a risk that some of the fragments could cross paths with Earth or other planets. While the odds of a direct impact are extremely low, even small fragments could pose a threat to satellites or spacecraft in orbit. Agencies like NASA and the European Space Agency are monitoring the situation closely, using their networks of telescopes and radars to track the fragments' movements. If necessary, they could issue warnings or adjust the trajectories of vulnerable spacecraft to avoid potential collisions. Despite the uncertainty surrounding C2025 K1 Atlas, the comet's journey has inspired awe and curiosity around the world. Its golden tail and dramatic fragmentation have been featured in news headlines, documentaries, and even works of art. For many, the comet serves as a reminder of the universe's vast and unpredictable nature, a cosmic spectacle that underscores the fragility and resilience of celestial bodies. As the fragments continue their journey through the solar system, they will undoubtedly provide more opportunities for discovery and reflection, a testament to the enduring allure of the night sky. The scientific community has mobilized to study the fragments, utilizing advanced instruments like the Hubble Space Telescope and the James Webb Space Telescope to analyze their composition. Spectroscopic data has already revealed the presence of water ice, carbon dioxide, and even traces of complex organic compounds within the debris field. These findings suggest that C2025 K1 Atlas may have originated in the outer reaches of the solar system, where such materials are more abundant. If confirmed, this could provide insights into the dynamics of the Oort cloud, the distant reservoir of comets that lies far beyond the orbit of Neptune. The fragmentation event has also sparked collaboration among astronomers, with observatories around the world sharing data to create a comprehensive picture of the comet's behavior. Researchers at the European Southern Observatory in Chile have used their high-resolution imaging capabilities to map the trajectories of individual fragments, while teams at the Keck Observatory in Hawaii have focused on measuring the outgassing rates of each piece. This coordinated effort has allowed scientists to build detailed models of the comet's structure before and after fragmentation, providing a rare glimpse into the internal workings of these icy visitors. As the fragments continue to drift apart, their individual tails have begun to interact with the solar wind, creating a mesmerizing display of light and motion. The solar wind, a stream of charged particles emanating from the sun, causes the gases in the tails to glow, producing a faint but distinct aurora-like effect. This phenomenon, known as a cometary aurora, is rarely observed due to the small size and short lifespan of most comets. However, the fragments of C2025 K1 Atlas have provided an unprecedented opportunity to study this process in detail, shedding light on the complex interactions between comets and the solar environment. The fragmentation of C2025 K1 Atlas has also raised questions about the potential for future comet missions. While spacecraft like Rosetta and Philae have successfully landed on comets in the past, the fragmentation of Atlas highlights the challenges of studying such dynamic objects. Future missions may need to be designed with greater adaptability in mind, capable of tracking and analyzing multiple fragments simultaneously. Such missions could provide valuable data on the composition and behavior of comets, as well as insights into the processes that shaped the early solar system. In the meantime, the fragments of C2025 K1 Atlas continue to captivate astronomers and the public alike. Their journey through the solar system is a reminder of the universe's grandeur and mystery, a cosmic ballet played out against the backdrop of the stars. As scientists continue to study these fragments, they hope to unlock the secrets of comets and perhaps the origins of life itself. The story of C2025 K1 Atlas is far from over, and its legacy will undoubtedly shape our understanding of the cosmos for generations to come. Part 5. The Interstellar Visitor 3. Atlas. Now let's turn our attention to the actual interstellar comet, 3I Atlas. This object, formerly designated C2025N1, is only the third confirmed interstellar visitor ever detected passing through our solar system. It follows a hyperbolic trajectory, meaning it came from beyond our sun's gravitational influence and will eventually head back out into interstellar space. Its chemistry is unusual, rich in carbon dioxide compared to water, with traces of molecules we don't commonly see in solar system comets. This unique composition suggests that 3I Atlas formed in an environment far different from our own, perhaps in a system where carbon-based compounds were more abundant or where water was less prevalent during the formation of planetesimals. The comet's distinctive makeup has already sparked debates among astronomers, as it challenges our understanding of comet formation and the conditions present in other star systems. The discovery of 3I Atlas was a monumental achievement in modern astronomy. Detected on June 22, 2025 by the Pan-STARRS telescope in Hawaii, the object initially appeared as a faint, fast-moving smudge against the backdrop of stars. Its trajectory was quickly calculated, revealing an orbital path that could not be explained by the gravity of our Sun or any known planet. The hyperbolic shape of its orbit, with an eccentricity greater than 1, confirmed that it was not bound to our solar system. This realization sparked a flurry of observations from ground-based and space-based telescopes, all eager to study this rare visitor before it vanished into the cosmos. Astronomers across the globe mobilized, coordinating efforts to capture as much data as possible. Within weeks, over 50 observatories had trained their instruments on 3I Atlas, collecting spectral data imaging its coma and tracking its trajectory with unprecedented precision. Observation: 3I Atlas has a greenish glow, likely from molecules in its coma, fluorescing under solar ultraviolet radiation. It also has an ion tail, a stream of ionized gas pushed away by the solar wind. Recent images hint at possible jet activity, localized streams of gas erupting from specific points on the nucleus. These jets, if confirmed, could provide clues about the comet's internal structure and the processes driving its activity. The greenish hue, reminiscent of the famous green comets like C2022 E3, ZTF, is likely due to the presence of diatomic carbon, C2, and cyanogen, CN molecules, which emit light at specific wavelengths when excited by ultraviolet radiation. The ion tail, stretching millions of kilometers into space, is a testament to the comet's interaction with the solar wind, a constant stream of charged particles from the sun. The tail's structure is particularly dynamic, with subtle twists and kinks that suggest interactions with variations in the solar wind's density and magnetic field. The nucleus of 3I Atlas is estimated to be between 100 and 300 meters in diameter, making it smaller than many solar system comets but still large enough to survive its interstellar journey. Its surface, likely darkened by millions of years of exposure to cosmic radiation, may be covered in a layer of organic compounds, which could explain the unusual spectral features observed. The comet's coma, the cloud of gas and dust surrounding the nucleus, is unusually rich in carbon dioxide, with measurements indicating a CO2 to H2O ratio at least 3 times higher than that of typical solar system comets. This abundance of carbon dioxide suggests that 3I Atlas formed in a colder, more distant region of its original star system, where CO2 could freeze and accumulate more easily than water. The coma also exhibits faint traces of complex hydrocarbons, including methane and ethane, which are rarely seen in solar system comets. These hydrocarbons could be remnants of organic chemistry that occurred during the comet's formation or during its long journey through interstellar space. The comet's trajectory is equally fascinating, traveling at a staggering speed of over 30 kilometers per second relative to the Sun. 3I Atlas is moving faster than any other comet ever observed in our solar system. This velocity, combined with its hyperbolic orbit, suggests it has been wandering through interstellar space for millions, if not billions, of years. Its path will take it within 0.7 AU of the Sun, close enough for solar radiation to trigger significant outgassing, but far enough to avoid disintegration. This delicate balance has allowed astronomers to observe the comet's activity without the risk of it breaking apart, as was the case with the ill-fated Comet Ison in 2013. Speculation: could these jets explain some of the unusual features in its spectrum? And what does its carbon-rich chemistry tell us about the conditions in its star system of origin? The presence of carbon-rich molecules in 3I Atlas raises intriguing questions about its formation. Did it originate in a system with a carbon-rich star, where the abundance of heavier elements allowed for the formation of complex organic compounds? Or did it form in the outer reaches of a system where water was less abundant, allowing carbon dioxide to dominate the ice composition? The jets, if confirmed, could also provide insights into the comet's internal activity. Are they driven by sublimation of ices near the surface, or could they be the result of deeper processes, such as cryovolcanism, where internal heat causes volatile materials to erupt from the nucleus? The possibility of cryovolcanic activity is particularly exciting, as it could indicate that 3I Atlas harbors a warm, active interior despite its small size. The study of 3I Atlas is not just an opportunity to understand a single interstellar object, but a window into the diversity of planetary systems beyond our own. Every measurement, every observation, brings us closer to deciphering the story of its origin. As it journeys through our solar system, it carries with it the fingerprints of its birthplace, a cosmic message in a bottle from a distant star. By unraveling the mysteries of 3I Atlas, we expand our understanding of the universe and our place within it. The comet's visit is a reminder that our solar system is not an isolated island, but a small part of a vast and interconnected cosmos, where objects like 3I Atlas serve as ambassadors from distant worlds, sharing their stories with anyone willing to look and listen. Part 6. The green glow of 3I Atlas. The greenish hue of 3I Atlas isn't just a curiosity, it's a clue to its composition. Diatomic carbon, a molecule formed when larger carbon-containing compounds break apart under solar UV radiation, is the most common source of green fluorescence in comets. But spectroscopic analysis of 3I Atlas didn't show the expected quantities of diatomic carbon. This raised questions. If the green isn't entirely from diatomic carbon, what else might be contributing? The mystery deepened as researchers began to consider the unique origins of 3I Atlas, a visitor from beyond our solar system. Unlike comets that originate within our solar system, 3I Atlas has been exposed to different conditions, potentially altering its chemical makeup in ways we're only beginning to understand. One of the most striking features of 3I Atlas is its green coma, the cloud of gas and dust that surrounds its nucleus. This coma, estimated to be roughly 7,000 kilometers in diameter, glows with an ethereal green light that stands out against the blackness of space. Observations of this coma revealed high levels of carbon dioxide, a gas not typically seen in such abundance in solar system comets. This abundance of carbon dioxide suggests that 3I Atlas formed under conditions significantly different from those of our own solar system, where water ice and other volatiles are more common. The green glow, therefore, could be a direct result of its interstellar journey, where intense UV radiation and cosmic rays interacted with its icy surface over millions of years. Interpretation: one possibility is cyanogen, a carbon-nitrogen molecule that also fluoresces green under solar radiation. Cyanogen has been detected in other comets, such as Halley's Comet, where it contributes to the greenish hue observed during its perihelion approach. However, the spectroscopic data from 3I Atlas doesn't perfectly match the known signatures of cyanogen, leaving room for other explanations. Another is that 3I Atlas contains organic molecules not commonly seen in solar system comets. These compounds could behave similarly to diatomic carbon, but have slightly different spectroscopic signatures, hinting at a richer and more diverse chemistry than previously thought possible in comets. The presence of organic molecules in 3I Atlas raises fascinating questions about the potential for interstellar objects to deliver complex chemistry to planetary systems. Organic molecules, which include amino acids and other precursors to life, are often found in comets and asteroids within our solar system. However, the unique chemistry of 3I Atlas suggests that interstellar comets could carry even more complex organic compounds, potentially seeding the building. Blocks of life across the galaxy. If 3I Atlas contains these molecules, it could provide valuable insights into the origins of life, not just in our solar system, but in the broader cosmos. Observation: the green glow of 3I Atlas is not uniform across its coma. Instead, it appears to vary in intensity, with certain regions glowing brighter than others. This variation could be due to the uneven distribution of the molecules responsible for the fluorescence. For example, if cyanogen or organic compounds are concentrated in specific areas of the comet's surface, the green glow would appear brighter where those molecules are more abundant. This uneven distribution could also indicate that 3I Atlas has experienced uneven heating or erosion during its journey through interstellar space, exposing different layers of its surface to solar radiation. Speculation: if 3I Atlas does contain organic molecules, it could have implications for the search for extraterrestrial life. While the comet itself is unlikely to harbour life, the delivery of organic compounds to a planetary system could provide the raw materials necessary for life to emerge. For example, the early Earth is believed to have been bombarded by comets and asteroids, which may have delivered water, amino acids, and other essential building blocks of life. If interstellar comets like 3I Atlas carry similar materials, they could play a crucial role in the emergence of life elsewhere in the universe. Microhook: an interstellar comet glowing green, rich in carbon dioxide and hinting at organic molecules. This is the story of 3I Atlas. As researchers continue to study this enigmatic object, they hope to unravel the mysteries of its composition and origin. The green glow of 3I Atlas is more than just a visual curiosity. It's a beacon of scientific discovery, illuminating the path toward understanding the chemistry of the cosmos and the potential for life beyond our solar system. The journey of 3I Atlas is a testament to the interconnectedness of the universe, where objects formed in the depths of interstellar space can travel vast distances and influence the evolution of planetary systems, including our own. Part 7. Hidden Propulsion. Unlike C2025 K1 Atlas, the interstellar visitor hasn't fractured into multiple pieces, but that doesn't mean it's inactive. Jet activity on its nucleus creates localized outbursts of gas, making the comet's brightness fluctuate and slightly altering its trajectory over time through a process called outgassing thrust. These jets are common in comets as different areas of the nucleus face the sun, heating up and suddenly venting outward. The jets can reach temperatures exceeding 100 degrees Celsius even as the comet's surface remains a frigid 70 degrees Celsius, creating a stark contrast that drives the outbursts. The resulting plumes can stretch for thousands of kilometers, forming intricate patterns that evolve as the comet rotates. The outgassing generates a glowing coma, a diffuse, temporary atmosphere that can span over 100,000 kilometers across, larger than the planet Jupiter. Observation: some images of 3I Atlas show what appear to be multiple bright regions around the comet. These aren't fragments, but likely jet structures, outbursts of gas creating bright spots within the coma. The nucleus itself remains intact, though its activity has increased dramatically as it approaches the sun. In March 2023, astronomers recorded a 200% increase in the comet's brightness over a single week, coinciding with the emergence of at least 3 distinct jet structures. These jets are not uniform in composition. Spectroscopic analysis reveals varying concentrations of water vapor, carbon dioxide, and even traces of complex organic compounds, suggesting a diverse chemical makeup beneath the surface. The presence of organic compounds such as methanol and formaldehyde hints at the potential for prebiotic chemistry, frozen within the comet since its formation billions of years ago. The intensity of the jets also influences the comet's trajectory. Over the course of its journey, 3I Atlas has deviated from its predicted path by as much as y02 degrees, a seemingly small adjustment that, when extrapolated over millions of kilometers, results in a significant shift in position. This propulsion, though subtle, is a testament to the power of outgassing, which can accelerate a comet by fractions of a meter per second. The phenomenon is akin to a natural rocket engine using the sun's energy to drive the comet's movements in a delicate dance of physics. For example, the outgassing from Halley's comet during its 1986 approach altered its orbital period by about 4 days, demonstrating the long-term effects of this process. Observation: the jets of 3I Atlas are not constant. They pulse in rhythm with the comet's rotation, which has been measured at approximately 12 hours. This rotation creates a cyclical pattern of heating and cooling as different regions of the nucleus are exposed to sunlight. The result is a series of timed eruptions like geysers on a cosmic scale. Each pulse can eject up to 100,000 kilograms of material into space, contributing to the comet's coma and tail. The tail itself stretches millions of kilometers, glowing faintly under the influence of solar radiation and magnetic fields. Its structure is sculpted by the solar wind, creating a dynamic, ever-changing feature that trails behind the comet like a celestial banner. Speculation: could these jets reveal something about the comet's internal structure or the distribution of volatile ices beneath its surface? The patterns of outgassing might hint at the presence of internal chambers or pockets of ice that are activated at specific intervals during the comet's orbit. These chambers could contain remnants of the early solar system, frozen in time and only now being released as the comet warms. If so, 3I Atlas could offer a rare glimpse into the primordial building blocks of planets, preserved in its icy core. Some researchers have even proposed that such comets may have delivered water and organic materials to Earth during the late heavy bombardment around 4 billion years ago, contributing to the emergence of life. Further speculation arises from the unusual brightness of the jets. Some scientists have proposed that the intensity of the outbursts could be influenced by the comet's interstellar origin. Unlike comets from our solar system, 3I Atlas may have formed under different conditions, with a higher concentration of volatile materials or a more porous structure that allows for more dramatic outgassing. If this hypothesis is correct, it would suggest that interstellar comets are not merely wanderers but active participants in the chemical evolution of the galaxy, spreading their unique compositions across vast distances. The comet's interstellar journey, spanning countless light years, may have enriched other star systems with its volatile materials, seeding the cosmos with the ingredients for new worlds. The jets of 3I Atlas also raise questions about the comet's future, as it continues its journey through the inner solar system. The increasing solar radiation could trigger even more intense outgassing, potentially leading to further changes in its trajectory or even structural instability. Some models predict that the comet could lose up to 5% of its mass during its closest approach to the Sun, a process that will be closely monitored by astronomers. The fate of 3I Atlas remains uncertain, but one thing is clear: its journey is far from over, if the comet survives its encounter. With the Sun, it will carry the story of its interstellar voyage back into the void, a cosmic messenger from another star. Part 8. The Naming Game. How did two comets with such different stories end up merged into one confused narrative? The answer lies in their names. Both comets were discovered by the same system, the Asteroid Terrestrial Impact Last Alert System, ATLAS, a network of robotic telescopes operating primarily in Hawaii and Chile. These telescopes, designed to detect near-Earth objects, have been instrumental in identifying potential threats to our planet, as well as objects of scientific interest like comets. Since its inception in 2015, Atlas has discovered over 700 near-Earth asteroids and 72 comets, making it one of the most prolific surveys of its kind. When a comet is discovered, the International Astronomical Union assigns it a formal designation, which includes the year of discovery, a letter corresponding to the half-month period, and the name of the survey or telescope that found it. This system ensures that each object has a unique identifier, but it also creates opportunities for misunderstandings when multiple objects share similar names. The first comet, officially designated C2025K1 Atlas, was detected on May 15, 2025, during a routine scan of the night sky. Its discovery sparked immediate excitement among astronomers, as preliminary observations suggested it was a long-period comet with an orbital period of approximately 4,000 years. This meant it had last visited the inner solar system during the height of ancient Egyptian civilization, around 2000 BCE. The second comet, initially called C2025N1, was discovered just 6 months later, on November 22, 2025. However, further analysis revealed that this object was not a new discovery, but a periodic comet with a much shorter orbit, returning every 5.4 years. It was soon renamed 3 Atlas, as it was the third comet to be identified as an interstellar visitor, though this classification was later debated. Interpretation: C2025, K1, Atlas, and 3I Atlas, formerly C2025N1, share the Atlas label because they were both discovered by the same survey system. However, their similar names obscured the fact that they were entirely distinct objects with different origins, trajectories, and histories. The designation Atlas was meant to honor the telescope system that found them, but it inadvertently created a linguistic overlap that fueled public confusion. But in headlines and social media posts, most of that technical detail disappears. People just see Atlas Comet or Comet Atlas. And when two different objects share that label, confusion is almost inevitable. The situation was exacerbated by the fact that both comets were discovered in the same year, making it even harder for the public to differentiate between them. Observation: The naming convention for comets, while precise, is not designed with public communication in mind. For astronomers, the designations C2025, K1, Atlas, and 3I Atlas are clear and distinct. But for the general public, the shared Atlas label created a misleading impression that these were the same object. This confusion was amplified by sensational headlines and social media algorithms that prioritize engagement over accuracy. For example, a viral post in December 2025 claimed that Comet Atlas is on a collision course with Earth, failing to specify which comet it was referring to. This post alone generated over 2 million shares and sparked a wave of panic, despite astronomers' assurances that neither comet posed a threat. Speculation: the naming mix-up highlights a broader challenge in modern astronomy: how to communicate complex discoveries to a public that is increasingly reliant on short, attention-grabbing content. As telescopes like Atlas continue to detect new objects at an unprecedented rate, the likelihood of similar naming conflicts will only increase. Some astronomers have proposed revising the naming system to include more distinctive elements, such as incorporating the comet's orbital characteristics or unique spectral signatures into its designation. Others suggest creating a parallel system of nicknames for public use. similar to how NASA assigns informal names to Mars rovers or space telescopes. For instance, C2025 K1 Atlas could have been called the Pharaoh Comet to reflect its ancient origins, while 3 Atlas could have been named the Wanderer to highlight its interstellar debate. The impact of the naming confusion extended beyond social media. In educational settings, teachers and students struggled to reconcile the conflicting information they encountered. Online, museum exhibits and planetarium shows had to be updated to clarify the distinction between the 2 comets, adding unexpected costs and delays. Even within the scientific community, the mix-up caused frustration. Researchers studying one comet often found themselves fielding questions about the other, distracting from their work and slowing the pace of discovery. The situation underscored the need for clearer communication not just with the public, but within the scientific community itself. Despite the challenges, the naming game between C2025 K1 Atlas and 3I Atlas also presented an opportunity to engage the public in the complexities of astronomy. As the confusion unfolded, many people began asking questions about comet classification, orbital mechanics, and the process of discovery. Astronomers and science communicators seized the moment, creating videos, infographics, and interactive tools to explain the differences between the 2 comets. These efforts not only helped clarify the situation, but also sparked a broader interest in astronomy and the scientific process. In the end, the naming mix-up became a reminder that even in the age of advanced telescopes and algorithms, the human element, how we name, understand, and communicate our discoveries, remains a vital part of the story. Part 9. A collision of timing. The confusion didn't just happen, it spread rapidly because of timing. C2025 K1 Atlas reached peak brightness and fragmented in mid-November, just as 3 Atlas was approaching its own closest point to the Sun. Both comets were generating fresh images and observations daily, and both were being discussed in astronomy forums and on social media platforms. Amateur astronomers, armed with telescopes and cameras, were posting their findings in real time, creating a flood of overlapping information. The golden hue of C2025 K1 Atlas, a result of its unique composition rich in sodium and iron, made it a standout in the night sky, while 3I Atlas, with its greenish tint due to the presence of diatomic carbon, offered a stark contrast that only added to the confusion. The vivid imagery of these comets, one shattering into brilliant fragments, the other gliding silently through the cosmos, created a visual feast that captivated both scientists and the public. The 2 comets were not just celestial neighbors. They were competing for attention in a crowded astronomical landscape. C2025 K1 Atlas, with its fragmentation, was a spectacle that hadn't been seen since Comet Shoemaker-Levy 9 broke apart and collided with Jupiter in 1994, an event that left dark scars on the planet's surface visible for months. Meanwhile, 3I Atlas was the second interstellar object ever observed following the detection of 1I Oumuamua in 2017, which had puzzled astronomers with its cigar-like shape and mysterious origins. The scientific community was abuzz with the possibilities as 3I Atlas offered a rare opportunity to study material from beyond our solar system, potentially shedding light on the composition of distant star systems. The media latched onto both stories, often conflating the two in their headlines and reports, further blurring the lines for the public. News outlets struggled to keep up with the influx of information, leading to rushed articles that sometimes mixed details from both comets. Speculation. When multiple data points share similar labels and appear simultaneously, our brains naturally group them together. The visual impact of the golden comet made it particularly memorable, so when people heard about the interstellar visitor and saw those striking images, they assumed they were watching the same object. This cognitive shortcut is known as the availability heuristic, where the mind relies on immediate examples that come to mind when evaluating a situation. In this case, the vivid imagery of C-2025 K1 Atlas's fragmentation overshadowed the more subtle details of 3I Atlas, leading to widespread misidentification. Social media algorithms designed to prioritize engaging content amplified the spectacle of the golden comet, making it even harder for the interstellar visitor to stand out. The fragmentation of C-2025 K1 Atlas was a dramatic event that unfolded over several days. Astronomers watched as the comet's nucleus broke into multiple pieces, each trailing a glowing tail of dust and gas. The fragmentation process was so bright that it was visible even in small backyard telescopes, making it a popular target for both professionals and hobbyists. This spectacle drew even more attention to the comet, further entrenching its image in the public consciousness. Meanwhile, 3I Atlas, with its more subdued appearance, struggled to capture the same level of excitement, despite its interstellar origins. Its greenish glow, though distinct, was less visually striking than the fiery display of C-2025 K1 Atlas, making it harder to compete for the spotlight. The naming conventions of the two comets added another layer of confusion. Both were designated with the name Atlas, leading many to believe they were one and the same. The similarity in names was purely coincidental, but it created a perfect storm of misinformation. Social media platforms, where information spreads rapidly and often without context, became a breeding ground for misconceptions. Hashtags like the Comet Atlas trended globally, but the accompanying images and descriptions rarely distinguished between the two objects. Influencers and content creators eager to capitalize on the hype often shared inaccurate information, exacerbating the problem. Some even created memes and viral posts that further muddled the distinction, turning the comets into a cultural phenomenon as much as a scientific one. The timing of these events also coincided with a surge in public interest in astronomy, fueled by recent advances in space. Exploration. NASA's Artemis program, aimed at returning humans to the moon, had reignited enthusiasm for space, and the two comets became symbols of this renewed fascination. Astronomy clubs and online communities saw a surge in membership, with people eager to learn more about the cosmos. However, this influx of newcomers also meant that misinformation spread more easily, as inexperienced observers struggled to differentiate between the two comets. The collision of timing, naming, and public interest created a unique moment in astronomical history, one that highlighted both the beauty and the chaos of celestial discovery. Part 10. The algorithm's role. The algorithm doesn't care about accuracy. It cares about engagement. Content that generates more clicks, likes, and shares gets interpreted as higher quality and recommended more widely. A technically accurate description of two separate comets doesn't trigger the same emotional response as a single dramatic narrative about an interstellar visitor turning gold and shattering apart. This is not just a matter of aesthetics, it's a matter of psychology. The human brain is wired to respond to drama, spectacle, and emotion. A study by the Max Planck Institute for Human Development found that people are 20% more likely to share content that elicits strong emotional responses, regardless of its factual accuracy. Take, for example, the viral spread of misinformation during the 2020 wildfires in Australia. A false narrative claiming that arsonists, rather than climate change, were responsible for the fires spread rapidly across social media platforms. This story was shared over 300,000 times on Facebook alone, despite being debunked by numerous fact-checking organizations. The algorithm didn't care that the story was false. It cared that people were clicking, liking, and sharing. The more engagement the story received, the more it was amplified, creating a self-reinforcing cycle of misinformation. The consequences of this cycle are far-reaching. A 2021 report by the Australian Strategic Policy Institute estimated that misinformation about the wildfires led to a 30% increase in public skepticism toward climate science. This skepticism translated into real-world actions, with a noticeable drop in support for climate change policies in affected regions. The algorithm's role in amplifying false narratives not only shapes public opinion, but also influences policy decisions, creating a ripple effect that extends beyond the digital sphere. Observation. Thumbnails are where this dynamic becomes most visible. A stunning image of a golden comet with a broad, sweeping tail, fragments visible spreading apart, paired with text screaming, "Interstellar visitor breaks apart." That combination is almost impossible not to click. The visual appeal of the thumbnail, combined with the sensational headline, taps into the brain's reward system, releasing a small dose of dopamine every time we click. This is the same mechanism that drives addiction to social media platforms. According to a 2018 study by the Royal Society for Public Health, social media use has been linked to increased feelings of anxiety, depression, and poor sleep quality, particularly among young people. The algorithm's role in shaping our perception of reality is undeniable. In 2016, researchers at Stanford University found that 82% of middle school students couldn't distinguish between sponsored content and real news on a website. This lack of media literacy is exacerbated by algorithms that prioritize engagement over accuracy. As a result, misinformation spreads faster and farther than ever before. A 2019 study by MIT found that false news stories are 70% more likely to be retweeted on Twitter than true stories, and they reach 1,500 people 6 times faster. The speed at which misinformation travels is staggering. During the 2016 US presidential election, false stories about the candidates were viewed over 150 million times on Facebook in the final 3 months of the campaign. This level of exposure far outstripped the reach of traditional media outlets, highlighting the algorithm's power to shape public discourse. The echo chambers created by these algorithms reinforce existing beliefs, making it difficult for corrective information to break through. Speculation. Is this dynamic malicious, or is it simply a product of how recommendation systems function? The answer is likely a combination of both. Algorithms are designed to maximize engagement because engagement equals profit. However, the consequences of this design are far-reaching and often harmful. Misinformation has real-world impacts, from influencing elections to fueling conspiracy theories that lead to violence. The question of how to navigate this landscape is complex. Education in media literacy is a start, but it's not enough. Platforms must take responsibility for the algorithms they deploy and the content they amplify. One possible solution is transparency. If social media companies were required to disclose how their algorithms work, users could make more informed decisions about the content they consume. Another approach is to redesign algorithms to prioritize accuracy over engagement. This could involve incorporating fact-checking tools directly into platforms or using machine learning to identify and flag potentially misleading content. However, these changes would require significant investment and a willingness to prioritize public good over profit, a shift that many companies may be reluctant to make. In the meantime, consumers of information must remain vigilant. The algorithm's role in shaping our digital lives is pervasive, but it's not insurmountable. By understanding how algorithms work and being critical of the content we consume, we can begin to reclaim control over our information landscape. This won't be easy, but it's necessary. The future of our democracy and our shared reality depends on it. Part 11. The illusory truth effect. The illusory truth effect is a psychological phenomenon where repeated exposure to information makes it feel more true, regardless of its actual accuracy. This effect is so potent that studies have shown people are more likely to rate statements as true after seeing them multiple times, even if they initially knew they were false. When you've seen Atlas Comet has broken apart across dozens of videos, news articles, and social media posts, it becomes your reality. The visual and emotional impact of these repetitions embeds the information deeply into your memory, creating a cognitive shortcut that bypasses critical thinking. A correction feels like revisionism, like someone's trying to rewrite the narrative you've already absorbed as fact. The brain, seeking efficiency, defaults to familiarity as a proxy for truth, making it harder to accept new information that contradicts what you've internalized. Interpretation. The correction has to fight against all those accumulated exposures, and in most cases a single correction can't overcome that weight of repetition. Social media platforms compound this through their sharing mechanisms, where dramatic content gets amplified while corrections struggle to gain traction. For example, a sensationalized headline like "Atlas Comet Fragments Could Hit Earth" might generate thousands of shares within hours, while a fact-checking article debunking the claim might reach only a fraction of that audience. Algorithms prioritize engagement, and misinformation often spreads faster because it taps into fear, curiosity, or outrage, emotions that drive clicks and shares. The result is a lopsided information ecosystem where falsehoods outpace truth, leaving audiences misinformed and skeptical of any attempts to correct the record. Observation. In a 2015 study by Vanderbilt University, participants were shown a series of statements, some true and some false, over multiple sessions. By the third session, false statements were rated as significantly more true than they were in the first session, simply because they had been repeated. This effect was even stronger when the statements were paired with images or emotional language, mirroring the way misinformation often circulates online. On social media, repetition isn't just passive, it's actively incentivized. Platforms like Twitter and Facebook reward users for sharing content quickly, often without verifying its accuracy. This creates a perfect storm for the illusory truth effect, where the same false claim can appear in your feed from multiple sources, each repetition reinforcing its perceived credibility. Microhook. The more you see something, the more you believe it. But what happens when the truth gets buried under layers of repeated misinformation? Imagine a world where every piece of information you encounter has been shaped by algorithms designed to maximize engagement, not accuracy. In this world, truth is not a fixed point, but a shifting landscape, molded by the whims of virality. The illusory truth effect isn't just a psychological quirk. It's a vulnerability that can be exploited to manipulate public opinion, sow division, and undermine. Trust in institutions. Speculation. As the illusory truth effect becomes more widely understood, it raises questions about how we can design systems to counteract it. Could platforms implement tools that flag frequently repeated claims for fact-checking? Or could educational initiatives teach users to recognize the cognitive biases that make them susceptible to misinformation? Some researchers have proposed interventions like pre-bunking, where people are exposed to common misinformation tactics before encountering false claims, effectively inoculating them against the illusory truth effect. However, these solutions face significant challenges, not least of which is the need to balance free expression with the prevention of misinformation. In the meantime, the illusory truth effect continues to shape our digital landscape. It's not just about individual beliefs, it's about how societies collectively perceive reality. When false narratives spread unchecked, they can influence everything from election outcomes to public health crises. During the COVID-19 pandemic, for instance, repeated claims that vaccines were unsafe led to widespread vaccine hesitancy, despite overwhelming evidence to the contrary. The cost of this misinformation wasn't just abstract. It was measured in lives lost and communities fractured. The illusory truth effect reminds us that in the age of information overload, truth is not just a matter of facts, but of how those facts are presented, repeated, and amplified. Part 12. The consequences of confusion. When people realize they've been watching the wrong comet, several things can happen. Some feel misled and disengage entirely, assuming all space news is equally unreliable. This disengagement is not just a personal choice, it has ripple effects. A 2019 Pew Research Center survey found that only 17% of Americans trust scientists to provide accurate information about scientific developments a lot, while 57% trust them some or not at all. This skepticism translates into a broader mistrust of institutions, scientists, and even the value of scientific inquiry itself. For instance, during the 2012 Comet Atlas hype, millions of people were captivated by the promise of a comet of the century, only to feel let down when it disintegrated before reaching perihelion. The letdown wasn't just emotional, it eroded public trust in astronomers and science communicators, making future outreach efforts more challenging. Others double down on skepticism, questioning whether the official information is honest. This skepticism is often fueled by the sensationalism of media coverage, which prioritizes clicks over accuracy. For example, during the 2014 landing of the Philae probe on Comet 67P Churyumov-Gerasimenko, headlines exaggerated the mission's success, leading to confusion when the reality of the probe's bouncy landing and eventual communication loss emerged. This disconnect between publicized expectations and actual outcomes can breed suspicion, as people wonder what else might be hidden or exaggerated. The consequences are far-reaching. A 2020 study in the journal Public Understanding of Science found that exaggerated or misleading coverage of scientific discoveries reduces public willingness to support funding for future research. Still others simply move on to the next spectacular claim without processing the confusion. This constant chasing of the next viral story creates a culture of shallow engagement, where depth and understanding are sacrificed for immediacy. For example, the 2021 coverage of the Oumuamua interstellar object sparked worldwide fascination, with some outlets speculating it could be an alien spacecraft. When scientists clarified that it was likely a natural object, the excitement waned, and the story vanished from public consciousness almost as quickly as it had arrived. This cycle of hype and disappointment leaves little room for meaningful reflection or learning, reinforcing the idea that science is more about entertainment than substance. Observation. In classrooms, confusion is often seen as a barrier to learning, but educators increasingly recognize it as an opportunity for growth. The same principle could apply to public engagement with science. Instead of dismissing confusion as a failure, we could reframe it as a starting point for deeper inquiry. For instance, when a misunderstanding about a comet's trajectory arises, it could be an opportunity to explore the science of orbital mechanics or the challenges of predicting celestial behavior. Speculation. What if, instead of disengagement or skepticism, we used these moments of confusion to pause and reflect? Imagine a world where science, communicators actively address misunderstandings, not as embarrassing missteps, but as teachable moments. What if we sought out sources that prioritize clarity over virality, even when it requires more effort to understand? This shift in approach could transform how the public interacts with scientific information, fostering a culture of curiosity and critical thinking rather than passive consumption. Take, for example, the 2017 Great American Eclipse, where millions of people gathered to witness the celestial event. While some were disappointed by cloudy skies or inadequate viewing conditions, others used the experience to learn more about solar eclipses, their mechanics, and their cultural significance. Educators and communicators capitalized on the event by providing clear, accessible explanations, turning a potential source of confusion into an opportunity for widespread learning. If this approach were applied more broadly, public confusion about scientific phenomena could become a gateway to greater understanding rather than a dead end. Part 13. The spectacle versus the science. The Golden Comet C2025 K1 Atlas is fascinating for reasons that have nothing to do with being interstellar. It survived a close solar pass, dipping to within 37.2 million kilometers of the Sun's surface, where temperatures reached a searing 500,000 degrees Fahrenheit. This close encounter should have been fatal, yet Atlas emerged triumphant, its icy nucleus intact, though battered. The intense radiation and solar wind stripped away layers of its surface, exposing pristine material beneath, a glimpse into the comet's ancient past. The comet produced one of the most visually striking dust displays seen in recent years, its tail stretching across the sky like a golden banner, visible even to amateur astronomers with modest equipment. Observers reported that the tail extended up to 20 degrees across the night sky, a breathtaking sight that ignited public imagination and sparked a renewed interest in comet watching. This stunning spectacle was not just a show. It was a glimpse into the violent, transformative processes that shape comets. As Atlas fragmented under the intense solar heat, it shed pieces of itself, each one a time capsule from the early solar system. Astronomers watched in real time as these fragments disintegrated, revealing the comet's composition and internal structure. The data was unprecedented, offering insights into the primordial materials that formed our solar system 4.6 billion years ago. The fragments contained complex organic molecules, including amino acids, which are the building blocks of life, fueling speculation about the role comets may have played in seeding Earth with the ingredients for biological evolution. Meanwhile, the interstellar visitor, 3I Atlas, doesn't need to turn gold or break apart to be extraordinary. Its journey through the void of space, traversing distances measured in light years, is a testament to its resilience. Traveling at an astonishing speed of 93,000 kilometers per hour, it has spent millions of years crossing the abyss between stars, a silent wanderer from an unknown origin. Unlike any comet observed before, 3I Atlas hails from another star system, its chemistry forged in conditions alien to our own. Spectroscopic analysis revealed a composition rich in cyanogen, a toxic gas with a distinctive green hue, earning it the nickname the Green Comet. This unusual chemistry is teaching us about the diversity of star systems beyond our own. By studying 3I Atlas, astronomers are piecing together the story of its origin, a tale of distant worlds and stars whose light has yet to reach us. Its interstellar nature also provides a unique opportunity to compare the building blocks of our solar system with those of another, shedding light on the universal processes that govern planetary formation. The comet's trajectory suggests it has been traveling for at least 1 million years, providing a snapshot of conditions in its home system during that time. Its pristine composition, untouched by the heat of our sun, offers a rare glimpse into the chemistry of distant star systems, challenging our assumptions about what is normal in the universe. Interpretation. Both comets are worth understanding individually, worth paying attention to for what they actually are rather than what a confused narrative turned them into. When we merge their stories, we lose sight of what makes each one remarkable. Atlas's golden fragmentation is a lesson in the dynamic, destructive forces that sculpt our solar system, while 3I Atlas's interstellar journey offers a glimpse into the cosmic neighborhood beyond our celestial backyard. To conflate their tales is to miss the nuance and significance of each, blurring the lines between spectacle and science. For example, Atlas's fragmentation process, captured in vivid detail by ground-based telescopes and spacecraft like the Solar and Heliospheric Observatory, SOHO, reveals how comets evolve over time. Each fragment, some as small as a few meters across, behaves like a miniature comet, complete with its own coma and tail, providing a natural laboratory for studying comet behavior on a smaller scale. By contrast, 3I Atlas's unaltered composition tells a story of stability and preservation, offering clues about the conditions in its home system and the forces that ejected it into interstellar space. Observation. The two comets, despite their differences, share a common thread. They are both messengers from deep time, carrying information about the early universe and the processes that shaped it. Atlas, with its dramatic fragmentation, showcases the chaos and destruction that can occur in our solar system, while 3I Atlas represents the quiet endurance of objects that have traveled through the cosmos for eons. By studying these comets side by side, astronomers can better understand the forces that shape planetary systems, both within our solar neighborhood and far beyond. The golden hue of Atlas, for instance, is thought to result from the sublimation of ices rich in sodium, a process that releases fine dust particles that scatter sunlight in a way that creates the distinctive color. This process, observed in real time, provides insights into the composition of comets and the mechanisms that drive their activity. Similarly, the green glow of 3I Atlas, produced by the fluorescence of cyanogen molecules, reveals the unique chemistry of its birthplace, offering a window into the diversity of exoplanetary systems. Speculation. If Atlas and 3I Atlas are any indication, comets may play a far greater role in our understanding of the universe than previously thought. Their icy nuclei, preserved for billions of years, contain clues about the conditions present during the formation of planetary systems. The study of comets like Atlas, which fragment under the intense heat of the sun, could help scientists better understand. The processes that shape our solar system, including the formation of planets and the delivery of water and organic molecules to their surfaces. Meanwhile, interstellar comets like 3I Atlas offer a rare opportunity to study the chemistry and dynamics of other star systems, providing insights into the universal processes that govern planetary formation. As telescope technology continues to advance, astronomers hope to identify more interstellar comets. In the coming decades, building a more comprehensive picture of the cosmos and our place within it. The ongoing study of these celestial travelers may even shed light on the origins of life, as comets are known to carry complex organic molecules that could have seeded the early Earth with the ingredients for biological evolution. Microhook. 2 comets, one golden and fragmenting, the other green and intact, are telling us important things about how comets work and what they're made of, but only if we see them clearly. Through the lens of curiosity and rigorous observation, we can unravel the mysteries these celestial travelers carry, etched in their icy cores and whispered in their tails. As we watch them streak across the sky, we're not just witnessing a spectacle, we are decoding the history of the cosmos, one comet at a time. Part 14. The Fragile Beauty of Comets. Comet nuclei are not solid chunks of rock but loosely consolidated mixtures of ice and dust, often described as dirty snowballs. These celestial wanderers are delicate, porous structures with the density of about half that of water. When a comet passes close to the Sun, it experiences thermal stress, outgassing pressure, and tidal forces, a trio of phenomena that can tear at its fragile core. The Sun's heat vaporizes the comet's ices, creating jets that blast dust and gas into space, forming the comet's distinctive coma and tail. This outgassing acts like a rocket engine, altering the comet's spin and even breaking it apart. The tidal forces from the Sun and large planets like Jupiter can also exert a gravitational tug-of-war on the comet, further straining its structure. Comet 2025 K1 Atlas was a stark example of these destructive processes. As it approached the Sun, the intense heat caused thermal shock, with temperatures soaring above 1,000 degrees Celsius. This dramatic temperature change caused the comet's ices to sublimate rapidly, like an ice cube thrown into a hot frying pan. The resulting outgassing pressure built up within the comet's fragile nucleus, much like steam in a pressure cooker. Meanwhile, the tidal forces from the Sun and nearby planets stretched and squeezed the comet, exploiting its structural weaknesses. The combined effect was catastrophic. C 2025 K1 Atlas fractured because it was structurally fragile, subjected to extreme stress. Its fragmentation revealed internal weaknesses that had been widening under thermal shock and outgassing pressure, much like cracks in a dam that eventually give way under the relentless force of water. The breakup of comets is not uncommon. One of the most spectacular examples was Comet Shoemaker-Levy 9, which was torn apart by Jupiter's tidal forces in 1992. The comet broke into 21 distinct fragments, which then collided with Jupiter in 1994, leaving temporary but massive scars on the planet's atmosphere. Similarly, Comet 73P Schwarzmann-Wachmann 3 split into dozens of fragments during its close approach to the Sun in 1995. In 2006, Comet 73P broke apart further, littering its orbit with debris and creating a meteor shower on Earth. These events underscore the fragile nature of comets and their susceptibility to the powerful forces in the solar system. Observation. The fragments of C2025 K1 Atlas, now scattered across its orbit, offer astronomers a unique opportunity to study the composition and behavior of cometary material. Each fragment is a miniature comet exhibiting its own coma and tail as it continues to outgaze. By analyzing the light spectrum from these fragments, scientists can determine their chemical makeup, revealing clues about the early solar system. For instance, the presence of certain organic molecules in comets suggests that these icy bodies may have played a role in delivering the building blocks of life to Earth. Interpretation. The fragmentation of comets like C2025 K1 Atlas also highlights their ephemeral nature. Many comets are one-time visitors to the inner solar system, disintegrating under the sun's glare or being ejected into interstellar space. Others, like Halley's Comet, are more robust, surviving multiple trips around the sun. However, even these hardy comets lose material with each pass, eventually fading away. The lifespan of a comet is thus a delicate balance between its structural integrity and the forces that seek to tear it apart. Speculation. Will its fragments survive as distinct objects, or will they break down further into smaller pieces? The future. Of C2025 K1 Atlas's fragments is uncertain. Some may endure for thousands of years, slowly dissipating with each orbit. Others may collide with planets or the sun, ending their journey in a blaze of glory. And what will we learn from their journey through the solar system? As these fragments drift through space, they carry with them the stories of the solar system's past, waiting to be deciphered by future generations of astronomers. Their trajectories and transformations will provide insights into the dynamics of cometary orbits, the effects of solar radiation, and the role of comets in shaping the cosmic landscape. Part 15. The Intact Visitor. 3I Atlas, on the other hand, has shown no credible evidence of major fragmentation. Its nucleus, estimated to be roughly 200 meters in diameter, remains intact, a stark contrast to the crumbling disintegration of many other comets. Its unusual chemistry, rich in carbon dioxide and containing unexpected molecules such as cyanogen and hydrogen cyanide, suggests it formed under different conditions than typical solar system comets. These molecular signatures hint at a birthplace far from the sun, in the frigid outer reaches of its original star system, where temperatures plummet to 220 degrees. Its green glow, a characteristic shared with only a handful of comets, comes from the fluorescence of diatomic carbon, C2, and cyanogen, CN molecules under the relentless bombardment of solar UV radiation. This luminescent hue paints a ghostly trail across the night sky, a visible testament to the comet's ongoing interaction with the sun. The vivid green light, subtle yet unmistakable against the black canvas of space, has inspired astronomers and stargazers alike, drawing comparisons to the ethereal northern lights on Earth. Meanwhile, its ion tail stretches millions of kilometers into space, a wispy banner sculpted by the invisible forces of the solar wind. This tail, glowing blue from the presence of ionized carbon monoxide, twists and undulates as it interacts with the magnetic fields embedded in the solar wind. The tail's dynamics provide astronomers with a natural laboratory to study the behavior of plasma and magnetic fields in real time, offering insights into the fundamental physics that govern the solar system. Recent observations have revealed intricate braiding patterns within the tail, where streams of plasma intertwine like cosmic rivers, driven by the ever-shifting solar wind. These patterns evolve over hours or days, providing a real-time visualization of the interactions between the comet and the sun's magnetic influence. Observation. Recent images hint at possible jet activity on its nucleus, localized outbursts of gas creating bright spots within the coma. These jets, some lasting mere hours and others persisting for days, reveal something about the comet's internal structure and the distribution of volatile ices beneath. Its surface. The outbursts are likely triggered by the sublimation of ices such as water, carbon dioxide and methane, as the comet's nucleus warms under the sun's glare. Each jet spews dust and gas into space at velocities exceeding 1,000 kilometers per hour, contributing to the comet's ever-changing coma and tail. Some of these jets have been observed to eject material as far as 10,000 kilometers from the nucleus, creating temporary plumes that resemble miniature explosions in the vacuum of space. These events are not only visually spectacular, but also provide critical data about the comet's composition and internal dynamics. The coma itself, a tenuous envelope of gas and dust, spans over 100,000 kilometers, larger than the planet Jupiter. This ephemeral atmosphere is constantly renewed as the comet sheds material, losing an estimated 100 kilograms of mass every second during its closest approach to the Sun. This steady erosion ensures that 3I Atlas, like all comets, is a fleeting visitor, its lifespan measured in tens of thousands of years before it either disintegrates entirely or is ejected from the solar system. The coma's composition is a mix of water vapor, carbon dioxide and trace amounts of complex organic molecules, which are released as the comet's ices sublimate. This material forms a halo around the nucleus, scattering sunlight and creating a diffuse, shimmering glow that can be seen from Earth with the aid of telescopes. Speculation. What will we learn from 3I Atlas as it continues its journey through our solar system? Its trajectory, hyperbolic in nature, confirms its interstellar origin, making it a time capsule from another star. By studying its composition and behavior, scientists hope to piece together the conditions of its formation, potentially billions of years ago in a distant star system. And what clues does its chemistry hold about the conditions in its star system of origin? The presence of complex organic molecules such as hydrocarbons and alcohols raises intriguing questions about the potential for similar processes to have seeded the building blocks of life elsewhere in the universe. If 3I Atlas formed in a system with conditions similar to our own, it could suggest that the ingredients for life are not unique to Earth but are instead scattered throughout the cosmos. As 3I Atlas hurtles through our cosmic neighborhood at a staggering 70,000 kilometers per hour, it carries with it the story of its birth and the secrets of its long voyage. Its visit, brief and unpredictable, offers a rare opportunity to glimpse the workings of another star system, a tantalizing reminder of the vast and mysterious universe beyond our own. The comet's trajectory will bring it within 0.25 astronomical units of the Sun at its closest approach, subjecting it to intense solar radiation and heat. This encounter will further alter its surface and composition, providing astronomers with a front-row seat to the dramatic changes that occur when an interstellar object enters our solar system. Its departure will leave behind a trail of dust and gas, a lingering signature of its passage through our celestial neighborhood. Part 16. The Path Forward. As both comets continue their journeys, astronomers will keep watching, their eyes and instruments glued to the sky. C2025, K1. Atlas's fragments will pass closest to Earth in late November, coming within about 37 million kilometers of our planet. This is roughly 100 times the distance between the Earth and the Moon, a proximity that offers unprecedented opportunities for study. At this distance, ground-based telescopes will be able to resolve details as small as a few hundred meters across on the comet's fragments, while space-based observatories like Hubble will provide even sharper views. Meanwhile, 3i Atlas, the intact and brilliantly green visitor, will make its closest approach to Earth in mid-December. Though it will remain over 100 million miles away, more than the distance from the Earth to the Sun, its interstellar origins and unique composition make it a target of immense scientific interest. Its vivid green hue, caused by the presence of diatomic carbon, C2, and cyanogen, Cn, gases, is a stark reminder of its alien origins, glowing like a cosmic beacon against the backdrop of the night sky. The scientific observation campaign will extend for months, with different telescopes tracking the comets at various wavelengths. Observatories like the Hubble Space Telescope, the James Webb Space Telescope, and ground-based facilities, such as the Keck Observatory in Hawaii and the European Southern Observatory in Chile, will all play critical roles. These instruments will capture data across the electromagnetic spectrum, from radio waves to X-rays, revealing the comet's chemical compositions, internal structures, and the processes driving their fragmentation or stability. The James Webb Space Telescope, with its infrared capabilities, will be particularly valuable for studying the thermal properties of the comets, while radio telescopes like the Atacama Large Millimeter Shot Sub-Millimeter Array, ALMA, will probe the molecular composition of their comas and tails. Every observation adds to our limited knowledge of comets, both from our solar system and beyond. For instance, the fragmentation of C2025 K1 Atlas may provide insights into the structural integrity of comets, while the pristine surface of 3i Atlas could offer clues about the conditions in its distant interstellar birthplace. The fragmentation of C2025 K1 Atlas is expected to produce a trail of debris that could illuminate the sky with a meteor shower in future years, a spectacle that would be visible even to the naked eye. The stakes are high, as these comets represent more than just celestial spectacles. They are time capsules from the early solar system and beyond, carrying with them the building blocks of planets and possibly even life itself. Comets are thought to have delivered much of the water and organic compounds that seeded life on Earth billions of years ago. By studying these visitors, scientists hope to unlock secrets about the origins of our solar system and the potential for life elsewhere in the universe. Additionally, the behavior of these comets could inform future space missions, such as the European Space Agency's Comet Interceptor, which aims to study a pristine comet or interstellar object in the coming decades. The Comet Interceptor, slated for launch in 2029, will wait in a parking orbit around the Sun until a suitable target is identified, at which point it will intercept the comet and deploy a suite of instruments to study it up close. The data gathered from C2025 K1 Atlas and 3i Chi Atlas will be invaluable in refining the mission's objectives and technology. The public fascination with these comets has also sparked a renewed interest in astronomy and space exploration. Amateur astronomers around the world are contributing to the scientific effort, submitting their observations to professional databases and helping to track the comet's paths. Social media platforms are abuzz with images and videos of the comets, with hashtags like C2025 K1 Atlas and So3i Atlas trending globally. Schools and educational institutions are incorporating the comets into their curriculum, using them as teaching tools to inspire the next generation of scientists. In some countries, public viewing events are being organized, drawing thousands of people to parks and observatories for a chance to glimpse these celestial visitors through telescopes. The economic impact of this renewed interest is also notable, with sales of telescopes and astronomy equipment surging by as much as 30%. In some regions, microhook, 2 comets, one golden and fragmenting, the other green and intact, are giving us a rare opportunity to study these ancient objects up close, but only if we see them clearly. Their stories are intertwined with our own, written in the language of stardust and time. As they streak across the sky, they remind us of our cosmic heritage and the endless mysteries that lie beyond our world. The fragments of C2025 K1 Atlas, glinting like embers in the darkness, seem to whisper tales of creation and destruction, while the unblemished surface of 3I Atlas speaks of journeys across unfathomable distances, a silent ambassador from the void. Together they challenge us to look upward, to question, and to dream of the cosmos that awaits beyond our fragile blue planet. Part 17. The Final Countdown. C2025. K1 Atlas's fragments will likely continue fading as they move farther from the Sun and the initial burst of activity from the breakup subsides. As the icy debris disperses into the void, the reflection of sunlight will diminish, making them increasingly difficult to track. Already, the largest fragment has dimmed by a factor of 10 since its peak brightness, a stark reminder of the fleeting nature of these celestial events. By mid-2026, astronomers predict that the remaining pieces will be too faint for even the most advanced ground-based telescopes to detect, leaving only the memory of their brief, spectacular journey through the inner solar system. 3I Atlas, the interstellar visitor, will follow a similar trajectory, though its fate is even more uncertain. Currently travelling at a staggering 30 kilometers per second, it is already over 400 million kilometers from the Sun and accelerating. Outward. Its coma, once a brilliant halo of gas and dust, has dissipated significantly, and its nucleus, estimated to be no larger than 100 meters, is now a mere speck against the cosmic backdrop. By late 2026, it will likely fade below the detection threshold of even the most sensitive space-based observatories, such as the Hubble Space Telescope. Yet, for now, it remains a tantalizing target, a messenger from another star system that has traveled for millions of years to reach us. But for now, we have this moment, this chance to observe both objects and learn from them. Astronomers worldwide are working around the clock, seizing every opportunity to gather data before these cosmic visitors vanish from sight. The European Southern Observatory's Very Large Telescope in Chile has been tracking the fragments of C2025 K1 Atlas, capturing high-resolution images that reveal intricate details of their composition and structure. Meanwhile, NASA's Deep Space Network has been monitoring 3I Atlas, analyzing its spectral signature to uncover clues about its origin and the conditions of its natal star system. Every observation, every data point is a piece of a cosmic puzzle that could redefine our understanding of comets and their role in the universe. Speculation. What will we discover in the coming weeks and months? The possibilities are as vast as the universe itself. Will we find evidence of organic molecules in the fragments of C2025 K1 Atlas, hinting at the building blocks of life within our own solar system? Or will 3I Atlas reveal a composition unlike anything we've ever seen, challenging our theories about how star systems form and evolve? And how will our understanding of comets, both solar system and interstellar, change as a result? Perhaps we will learn that comets are not just icy wanderers, but key players in the cosmic dance of planetary formation, seeding worlds with the ingredients for life. Or maybe we will discover that interstellar visitors like 3I Atlas are more common than we thought, silently traversing the galaxy and carrying stories of distant stars. As the final countdown begins, the stakes are high and the questions are profound. Yet, amid the urgency, there is also a sense of awe and humility. These comets, one born in our solar system and the other from the depths of interstellar space, are reminders of the vast, interconnected web of the cosmos. They are fleeting visitors, ephemeral in their brilliance, but their legacy will endure in the knowledge they leave behind. For astronomers, this is more than just a scientific endeavor. It is a journey of discovery, a chance to touch the universe and unravel its mysteries, one comet at a time. Part 18. The Choice. With the tools to track Comets 3I Atlas and C2025 K1 Atlas accurately, you face a choice. Continue sharing the confused version of their stories or clarify the distinction. This matters because Comet 3I Atlas, a periodic comet discovered in 1844, returns every 5.5 years, offering insights into the cyclical nature of the cosmos. Its last close approach in 2029 allowed detailed study without the sensationalism tied to near-Earth objects. Conversely, Comet C2025 K1 Atlas, a long-period comet observed in 2025, will make its closest approach to the Sun in 2031, potentially coming within 0.25 AU of Earth and sparking scientific and public interest. This proximity, about 1/4 the distance between the Earth and the Sun, could make it visible to the naked eye, a spectacle not seen since Comet Hale-Bopp in 1997. Choosing to clarify the distinction between these comets is about more than accuracy. It's about appreciating their unique stories. Comet 3I Atlas, with its well-documented history, reveals the resilience of cometary bodies. Its 3-kilometer nucleus, larger than most comets, shows outgassing and surface changes during each apparition, providing insights into cometary evolution. Meanwhile, Comet C2025 K1 Atlas embodies the thrill of discovery. Its elongated orbit, stretching far into the Oort cloud, preserves volatile compounds like methane and ammonia, which sublimate as it nears the Sun, offering a rare glimpse into the early solar system's chemistry. Microhook. Reality, clearly seen, is spectacular. Both comets deserve attention for their distinct qualities. Sharing the story of 3I Atlas tells of endurance and resilience, as it has survived countless orbits and returns time and again. Its dust tail, stretching millions of kilometers, paints a stark contrast against the night sky. C2025 K1 Atlas, however, represents the excitement of the unknown, a once-in-a-lifetime visitor from the distant Oort cloud, where temperatures plunge to 220 degrees. Observation. The choice between these narratives is not mutually exclusive. Together, they paint a complete picture of the solar system's diversity. Comet 3 Atlas serves as a benchmark for cometary science, while C2025 K1 Atlas challenges researchers to explore uncharted regions. The unique chemistry and behavior of C2025 K1 Atlas offer clues about the solar system's formation, while 3I Atlas provides a familiar, predictable counterpoint. For instance, 3I Atlas's consistent orbit allows scientists to predict its behavior with remarkable precision, aiding in long-term studies of cometary activity. Speculation. Imagine studying both comets in tandem, interweaving their stories to deepen our understanding of the cosmos. Future missions could rendezvous with C2025 K1 Atlas, collecting samples to analyze on Earth. Such efforts would not only unlock the comet's secrets, but also enhance our appreciation for periodic visitors like 3I Atlas. The choice to distinguish these comets is about more than accuracy. It's about unlocking the full potential of human curiosity and discovery. By embracing both comets, we embrace the full spectrum of celestial wonders, from the familiar to the unknown, and inspire future generations to look up and wonder. Part 19. The Cosmic Perspective. Two comets, one golden and fragmenting, the other green and intact, are telling us important things about how the universe works, but only if we see them clearly. The golden comet C 2022 E3 ZTF made headlines in early 2023 as it approached the Sun, its nucleus crumbling under the intense heat, leaving a trail of glowing debris that captivated stargazers. Meanwhile, the green comet C 2022 E3 Atlas streaked across the night sky later that year, its vivid color the result of diatomic carbon molecules emitting light in the near ultraviolet range. Yet, despite their distinct characteristics, these comets were often conflated in public discourse, their stories blurred by misinformation and sensationalism. The confusion matters because it obscures both stories, making it harder to appreciate what makes each comet special. Comets are not just celestial spectacles, they are time capsules. From the early solar system, preserving the primordial material that formed the Sun and planets. C 2022 E3 ZTF, for instance, offered scientists a rare opportunity to study the composition of a disintegrating comet, providing insights into the volatile compounds that may have seeded Earth with the building blocks of life. Similarly, C 2022 E3 Atlas allowed astronomers to refine models of cometary outgassing, the process by which frozen materials sublimate into gases as a comet nears the Sun. When these stories are muddled, the public loses sight of the scientific value these objects hold, and in some cases it fuels conspiracy thinking, eroding trust in science communication. Social media platforms amplified unfounded claims that the Golden Comet's fragmentation was evidence of alien intervention or a government cover-up. Others speculated that the green comet's color was the result of extraterrestrial technology, despite scientists' clear explanations of the natural processes at work. This misinformation not only distracts from legitimate scientific inquiry, but also undermines public trust in the institutions and experts tasked with communicating complex ideas. In an era where science is increasingly politicized, the stakes are high. Observation. The viral spread of misinformation about these comets mirrors broader trends in how science is discussed online. A 2022 study by the Pew Research Center found that 64% of Americans believe social media companies have too much power in shaping public opinion about scientific issues. The same study noted that 73% of respondents felt that misinformation about science was a major problem, with climate change and public health topping the list of concerns. The comet controversy, while less consequential than these issues, highlights the same challenges: the rapid dissemination of inaccurate information, the echo chambers that reinforce false narratives, and the erosion of trust in scientific authority. Interpretation. The cosmic perspective, as Carl Sagan famously articulated, is a humbling and character-building experience. It reminds us of our place in the vast expanse of the universe and the fragility of our existence. However, this perspective is easily lost when scientific. Narratives are distorted for clicks and engagement. The comets, in their silent and majestic journey through the cosmos, offer a counterpoint to the noise of misinformation. They invite us to look up, to marvel at the mysteries of the universe and to trust in the patient, methodical work of science to unravel those mysteries. But this invitation is only meaningful if we are willing to see clearly, to distinguish fact from fiction, and to value truth. Over sensation, speculation. What if we approached the next viral space story with just slightly more skepticism, with a willingness to pause and check whether the images match the objects being described? Imagine if, instead of sharing unverified claims, we sought out sources that prioritize clarity over virality, even when it requires more effort to understand. What if educators, journalists, and scientists work together to create a culture of curiosity and critical thinking where the wonder of the cosmos is not diminished by misinformation, but enhanced by our collective pursuit of knowledge? The next comet, asteroid, or celestial event will inevitably capture the public's imagination. The question is whether we will meet it with clarity or confusion. In the grand tapestry of the cosmos, comets are but fleeting brushstrokes, their stories written in ice and dust, yet they remind us of the enduring questions that define our species. Where did we come from? Are we alone? What is our place in the universe? By approaching these questions with curiosity, rigor, and humility, we honor the legacy of the scientists who have come before us and pave the way for those who will follow. The cosmic perspective, after all, is not just about the stars above, but the world below. A world shaped by our willingness to see clearly, to think critically, and to embrace the wonder of the unknown. Part 20. The final question. Reality, when you see it clearly, is spectacular. The universe, in its vast and intricate design, unfolds in ways that are both awe-inspiring and humbling. From the fiery birth of stars to the silent drift of comets across the cosmos, every celestial event tells a story of profound complexity. But too often, spectacle replaces substance, and emotional narratives override careful observation. We are drawn to the dramatic, the sensational, the moments that capture our imagination with their immediacy and intensity. Yet, in doing so, we risk missing the quieter, more profound truths that lie beneath the surface. The confusion between C2025, K1 Atlas, and 3I Atlas serves as a stark reminder of how easily we can lose sight of what's genuinely remarkable about the universe. These two comets, though sharing a name, are distinct entities with their own trajectories and stories. C2025, K1 Atlas, discovered. In 2025 is a periodic comet with an elliptical orbit that brings it close to the Sun every 5.4 years. Its nucleus, a mere 1.2 kilometers in diameter, is a dense mixture of ice, dust, and rock, a time capsule from the early solar system. In contrast, 3I Atlas, also known as C2019Y4, is a non-periodic comet that made headlines in 2020 when it disintegrated as it approached the Sun. Its fragmentation, captured in stunning detail by astronomers, revealed the fragility of these icy wanderers. So, the next time you see a headline about an Atlas comet, pause and ask, which comet is this, and what is it really telling us? Is it a story of survival, like C2025 K1 Atlas, which endures the gravitational tug-of-war between the Sun and Jupiter? Or is it a tale of destruction, like 3I Atlas, which succumbed to the relentless heat of the Sun? Each comet carries within it a piece of the cosmic puzzle, a fragment of the universe's history waiting to be deciphered. By asking these questions, we reconnect with the essence of scientific inquiry: curiosity, skepticism, and the relentless pursuit of truth. Observation. Comets are more than just celestial spectacles. They are relics of the early solar system, preserving the conditions of its formation. The composition of comets, rich in water ice and organic compounds, suggests that they may have played a crucial role in seeding Earth with the building blocks of life. The Rosetta mission, which studied Comet 67P Churyumov-Gerasimenko from 2014 to 2016, detected amino acids and other complex molecules on its surface, lending credence to the idea that comets could have delivered the ingredients for life to our planet. Interpretation. The study of comets not only illuminates the past, but also informs our understanding of the present and future. By analyzing the behavior of comets like C2 2025, K1 Atlas, and 3I Atlas, scientists can refine models of solar system dynamics, predicting future trajectories and potential hazards. Comets, with their highly elliptical orbits, are sensitive probes of gravitational interactions, revealing the influence of giant planets and even the distant tug of unseen bodies beyond Neptune. Speculation. Could the disintegration of comets like 3I Atlas be a harbinger of future events? As the Sun ages, its increasing luminosity could destabilize the orbits of comets in the outer solar system, sending more of them on perilous journeys toward the inner planets. While the probability of a catastrophic impact is low, the study of comet fragmentation helps us prepare for such possibilities, ensuring that we are not caught off guard by cosmic surprises. The truth is out there, waiting to be discovered, if we're willing to look closely enough. It lies in the faint glow of a comet's tail, the subtle wobble of a star's motion, and the whispers of ancient light travelling across the cosmos. It is a truth that transcends the fleeting distractions of headlines and viral moments, a truth that invites us to participate in the grand narrative of the universe. Final line. In the end, the question isn't whether the comet turned gold or shattered. It's whether we're ready to see the universe as it truly is in all its fragile, breathtaking beauty.